What is a vector valued function? In this video, we're going to talk about the definition of a vector valued function. We're going to talk about how to find the domain of a vector valued function, and also we're going to briefly talk about some of the geometry of vector valued functions. So to start, let's look at how we write the notation for a vector valued function. Typically, we use the notation r of t, and it's given by x of t, y of t, z of t. So each of these are called component functions. And really, it's just a function for what's going on for the x-coordinate, what's going on in the y-coordinate, and what's going on in the z-coordinate. Something that it's important to notice is that the inputs for these functions are real valued numbers. They're scalars, usually in R. Like it's a number like 5. I plug the number 5 into this function, and what do I get out? My range values, so my outputs, is a vector. And in this case, this is a vector valued function that's in 3 space. So I plug in a number like 3, and I get an output that's a vector in R3. So one way to think about this is a transformation from R space to R3. Let's look at an example. So let's say that we have a function r of t is equal to 1 over t square root t, t squared. So my x component is given by the function 1 over t, my y component is given by square root of t, and my z component is given by t squared. The first question that I want to ask myself is, what is the domain of this function? So for this function, the domain is going to be the values of t that are valid for each of these functions. For the first component function, we see that t cannot be equal to 0, because if t were equal to 0, then I would get an undefined result, 1 divided by 0. For the second component function, we see that t has to be greater than or equal to 0. We need positive values of t because we can't take negatives of square roots and still end up with real values. And then finally, for our last component of t, t could be, I'm going to write it like this, any real number. This is saying that t is an element of R, the real numbers. How can I use each of the inputs? Does that mean that I have 3 different domains? No, I don't have 3 different domains. All of these have to be valid. So it means that t cannot be equal to 0, and t has to be greater than or equal to 0. So in this case, my domain is going to be the t values that are strictly greater than 0, because I need to include both of these restrictions. It can't be equal to 0, and it also can't be negative. So the important part, the reason why we looked at vector valued functions, is in part because of the geometry of them. So let's consider this vector valued function, and we're going to generate a graph by hand. This is one of the more important types of vector valued functions, and then we're going to look at them, graphing them using some technology as well. So how am I going to graph this? By hand, I'm going to start just by plotting points. I'm going to make a table. And we see that for this vector valued function, we've restricted our domain to just being positive values of t. So I'm going to start with t equals 0. What happens when t equals 0? I plug 0 into my x component function, and I see that I get the sine of 0, which is 0. My cosine of t tells me that when I plug in 0, the cosine of t is 1, and t, is equal to 0. So the next value of t that I plug in, I could choose a half, I could choose any value that I want. If I choose 1 or a half, those make messy numbers for sine and cosine, so I'm going to use values that I like. With my next value, I'm going to choose pi over 2 as my next value, just because I know that the sine of pi over 2, I've moved along the circle until I get to 1. The cosine of pi over 2 is 0, and pi over 2 is my z. Next, let's move to pi, so we're continuing around the circle. The sine of pi is equal to 0 again. The cosine of pi is equal to negative 1, and my z value is at pi. And so on and so forth. I'll fill in a few more values of this. 3 pi over 2, I'm negative, I'm 0, and then I'll be at 3 pi over 2. And finally, we'll cycle back till we get to 2 pi, which is back where we started in terms of x and y. We'll be at 0 and at 1, but my z value has continued to grow and is now at 2 pi. Now I'm ready to attempt to draw a picture of this. This is one classic function that you are going to end up memorizing because it's hard to draw these by hand, right? It's hard to visualize what's going on. But let's start by plotting some points. We see that to start with, my x value is 0, my y value is 1, and my z value is 0. So I'm going to put that point right here. Then, as I continue on, I see that my x values are going to increase until they hit 1. My y values are going to decrease to 0, and my z values have gone up some. So really, in the xy plane, I'm starting to trace out the path of a circle. And as I trace out the path of this circle, my z value is increasing. So I've gone up in height as well. I'm up here. Continuing onwards, as my t value increased, I continued along the path of this circle, and my z value continued to increase. I continue to move around. By the time I get back here to 3 pi over 2, my z value has gone up even higher. And by the time I get back to my original point in terms of x's and y's, my z value has grown up very high. So if I were to connect these dots, we see that we're cycling outwards. And as we cycle in this circle, maybe the height was growing at a constant rate. It's hard to see this last one as it cycles back around, right? In my head, this was a beautiful picture. Really what's going on, this is a function that's a common function that's called a helix. And in this case, in the xy plane, it's helix with an x. Sorry, helix. In the xy plane, it's cycling around in a circle, and in the z plane, it's continuing to grow. And if I were to compress it down, it's a shape like a spring. It looks something like this, right? My scaling is just such that I don't really have the loop-de-loops happening in this scale. And it will continue to grow outwards. So this is an important vector value function that's a 3-state. Something to notice. Note that at each point along here, this is a different point for our t value. So the coordinates of this point are the coordinates for the second point in time was 1, 0, pi over 2. And this point in space happens when t equals pi over 2. So it's important to differentiate the t values we sometimes think of as time, and the x, y, z we think of as position in space. So you can think of this as a particle moving through time, and at different time points, we're going to have different locations in space. Because it's a vector valued function, my outputs in each case are these vectors. But typically these vectors, drawing these vectors, that's suppressed, that it's just confusing and makes the picture look messier when you add in all the vectors, that all of these points in space are actually the tips of vectors. That I will frequently, interchangeably, just draw the points in space rather than writing them as vectors. So that gets to the next distinction that I want to make, the difference between a path and the difference between a path and a curve. So the path is what was traced out here, is given by this particular function. So this function tells me what the path is, whereas the curve is actually these points in space. The distinction is important because different equations for this path can give the exact same curve, meaning that I might be able to write this function differently, and it would still trace out the same place in space. If I moved twice as fast along this curve, I would have a different path function, but the curve would still be the same curve.